right, so today we are going to look over the review for the Auroras unit. And I'm going to go through all of the questions and all of the answers with a little bit more of an explanation to help you guys out in case you get stuck on your review today. So the first section we're going to look at is how are the Auroras created? And the first question is, what is the source of energy for the Auroras? And of course, we know the sun is producing energy that's coming to Earth, but it's really the solar wind that actually creates the auroras. So the general answer I'm looking for here is the sun. If you have the sun, you're good. But more specifically, it's actually the solar wind, which is produced by the sun, which is creating our auroras. All right, question 2, what is fusion? So fusion happens when 2 or more protons fuse together to make a heavier element. And you can see here in our video that we've got these 2 elements coming together, going through fusion, and then producing this element plus a little neutron that is left over. All right, so why can fusion, question 3, why can fusion occur naturally in the core of stars but not in the center of Earth? So we know a few things. We know protons are positively charged and they repel one another because like charges repel. We also know the closer the protons get to one another, the higher the repulsion. The sun's core has a lot of heat and pressure due to all the sun's mass pressing down on the core. The forces are high enough to overcome this proton-proton repulsion and fuse the protons together to form helium. So again, we can see here in the picture what these arrows are showing is the mass kind of pushing down onto the center of the core and creating enough heat and pressure to force those protons together. All these guys in here are basically pushing way down on the mass and making it form a new element. All right, number 4, which elements are involved in fusion in our sun? So right now our sun is taking hydrogen and fusing it together to form helium. And as our sun gets older, it'll form heavier elements, but right now it's just hydrogen and helium. All right, let's look at number 5. What are the 2 products of fusion? So we know light comes off, and of course this is a picture of the different types of light that are coming off of the sun. We've got UV here, visible in the center, and infrared off to the side, all the way over to here. These are the 3 types of light that reach us, or electromagnetic radiation more specifically, and of course the solar wind, and that one's important to us because that is what's happening in the auroras. All right, so now we're going to look at the solar wind reaches Earth and how that interacts to form our auroras. So the first thing in our questions here is, what is the solar wind? And this is a picture of the solar wind, of course, and it is charged particles that are released by the sun. Now, of course, we already know the 2 main charged particles in the universe are electrons and protons. So those are the main particles coming off of the sun in the solar wind. But we also have alpha particles, which are really just helium nuclei stripped of the electrons. All right, so now let's look at why the auroras are at the poles but nowhere else. And of course, this is because the Earth has a magnetosphere, the magnetic fields, which has closed field lines around most of the Earth, and you can see them here. Here are closed field lines on this side and on this side. But there are open field lines at the poles, and this diagram really doesn't have them drawn in all that well, but they would look something like this at the poles. And it's here where the open field lines attract the charged particles. And of course, we know our little charged particles spiral down these field lines and into the atmosphere where they collide with the electrons in nitrogen and oxygen and create the auroras. All right, so what happens when the solar winds collide with nitrogen and oxygen in the Earth's atmosphere? What do we see in the night sky? And we're talking about the atomic level here, not just it produces the auroras, which of course we know what happens there. Okay, so we have the collision gives energy to the electrons in nitrogen and oxygen. So here we have the charged particles coming into our atmosphere, spiraling down those field lines and colliding with the electrons in nitrogen and oxygen. The electrons gain energy and move farther from the nucleus. And of course, we know they want to kind of move back in and become lower energy. So the electrons are not comfortable out there and they release energy as light and move back closer to the nucleus. All right, number 9, how is light produced? We're going to identify the subatomic particle, proton, neutron, or electron, how it moves, and how it creates light. And of course, we really went over this in the last question, but it's a really important topic. That's why it's kind of on here twice. So the electron gains energy and moves farther from the nucleus and then wants to move closer, so it releases energy as light. So here we can see in the picture, we've got an electron, a free electron colliding with our bound electron here. And then what happens is we're getting some energy. It moves farther out. And then to move back in, it gives off this little photon of light and moves back. All right, so oxygen produces the red and green lines in the auroras. And we also know nitrogen produces a purple, red, and blue overtones. How do these different elements produce different colors? So we know each element has a unique number of protons, neutrons, and electrons. And you can see here to the left, there are 3 Bohr models of carbon, silicon, and I think the last one's germanium. So it also has different energies for its energy levels. So even though these all have kind of energy level 1, energy level 2, and energy level 3, so here we've got energy level 1, 2, 3, and 4. Here we only have 1 and 2. Even though they all have 1 and 2 in common, the energy levels for 1 and 2 are different for different elements. So when for carbon, say an electron jumps from energy level 1 to energy level 2, say when silicon does the same thing or germanium does the same thing, they absorb different colors of lights because their energy levels are at different energies. Okay, so let me go back to reading. This means the atom's electron gains and loses different amounts of energy when moving in between energy levels and sublevels. And of course, the sublevels aren't this diagram. They're those S, P, D, F sections on the periodic table. So different energy light is a different color or a different type of electromagnetic radiation. All right. So is light a particle or wave or both? And we've kind of talked about how light is both a particle and a wave. And in different situations, it's going to show different properties. All right, so let's talk about as the wavelength of light increases, what happens to the frequency, which is the frequency, which is the number of peaks per second, and the energy. So my wavelength is increasing, so I'm getting longer and longer. So the frequency is going to decrease, and the energy is going to decrease as well. These two are always linked. Frequency and energy increase together or decrease together. It's a direct relationship. All right, let's look at 13. Here we have which of the following has the lowest energy and frequency and which would be the most damaging. Okay, so here we're looking at longest wavelength. So this one correlates, this box correlates to this line, this one to this line, and this one to this line. And I stretched it out because I added pictures. Yours is better lined up than mine. So what we have here, the first one on the top, this guy right here, is the lowest energy and frequency. So a longer wavelength is low energy and low frequency. Just like a big dog has low energy, generally speaking, and a low frequency of barking. The middle one's just kind of in the middle, right? We've got middle energy and middle frequency. And then, of course, our bottom line right here, which is a little faint, is a short wavelength, like a little dog. So it has the highest energy and frequency, just like a little dog has high energy and frequency of barking. All right, number 14. How does the light from stars help us identify elements in them? So we know each element produces a unique spectrum of colors, and this is because they have different energy levels, causing different colors of light to be absorbed and released. Scientists can collect the light from different stars, break it down using a diffraction grating, and determine which colors are in the spectrum. They can compare those colors to the colors given off by the elements and determine what's in the star. So you can see here on the top of the spectrum, this one right here, if you can't read that, it says hydrogen, and we can see the different spectral lines for hydrogen. So if we break down light from a star and compare those lines to the lines we see in the star, if all of those lines match up, hydrogen is in that star. All right, here we're writing electron configurations for the different elements. And of course, you need your periodic table here with the where the SPDF are located and the energy levels. So sodium is, let me show you. Let me get a periodic table up here. So sodium is right here in energy level 3, sublevel S. And so, of course, we're just going to start at the beginning. Here's 1S with 1, 2 blocks. So 1S2. 2s with 1, 2. Then we're going to move over to 2p, 1, 2, 3, 4, 5, 6, and then finally 3s1. And so you can see in the review, that's what I have written there, 1s2, 2s2, 2p6, 3s1. Now let's look at iron. So iron is in the Ds right here. You can see iron. So we're going to again start out 1s, 1, 2, 2s, 1, 2, 3s, 2p, 1, 2, 3, 4, 5, 6, 3s, 1, 2, 3p, 1, 2, 3, 4, 5, 6, 4s, 1, 2, and then 3d, 1, 2, 3, 4, 5, 6. All right, that's iron. So then, of course, I have that all written down here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. All right, our last one, bromine, which is our biggest element out of these three. Over here, so we can see we have everything that iron has. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, now out to 10, and then we're going to add on 4p5. 1, 2, 3, 4, 5, the fifth block. All right, let's start talking reactivity. So reactivity, of course, is how reactive an element is, and it's based off of atomic size. So the first thing we're going to do is draw an atom, including its subatomic particles. And we're going to create helium. So helium is atomic number 2. As we can see in this periodic table, it's on the top left. It's always the whole number, and it's always the smaller. So you can see this one is 4, this one is 2. My atomic number is 2. And the atomic number of 2 indicates there are 2 protons. And then since it's mass number of 4, we know the number of neutrons is this number rounded. 4 minus 2 gives us 2. And I don't expect you to have to know how to do that part on the test. You will not have to draw neutrons. I just want to explain where it's coming from. All right, so we're going to take our protons first and put them in. So here's our protons, and you can see I drew them in here in the nucleus because the protons are in the nucleus. Then my neutrons are neutral. These guys are also in the nucleus right here. And then last but not least, we have our electrons, and our electrons, since there's only 2 of them, go on that first energy ring, and so we just have our 2 electrons here. We wouldn't put them in energy level 2 until energy level 1 is filled. And it's 2, and then 8 is the maximum for the second energy level. And then the third, of course, has another 8, but we won't get much past that. All right, so we have been talking about this since the very beginning of the year, that metals hold their electrons loosely. This is why they are good conductors of heat and electricity, why they're malleable. All their different characteristics are because their valence level are held loosely. Whereas nonmetals, which are the opposite, they are dull and don't conduct electricity, is because they hold their valence level tightly. All right, so what do the following elements do in a reaction? So let's look at this. I just put a little diagram in here so we could see visually what happens to metals in a reaction, what happens to nonmetals. So in this case, if you think about sodium, let's first check if that's our metal or our nonmetal. So we can see here on the periodic table, sodium is over here. Sodium is a metal on our periodic table. And so, of course, then let's look at chlorine first before we go back. That is our nonmetal in this reaction that we're happening here. So we can see here sodium is giving electrons to chlorine. So sodium is losing electrons, and chlorine, our nonmetal, is gaining them. All right, so I just added a visual to help you guys with atomic size. What happens to atomic size on the periodic table? And you can see here it gets bigger as we go down and actually bigger as we head to the left. So when we talk about a down, it's going to increase. When we talk about across, we're always talking left to right, just like you read a book, and so it's going to decrease. All right, so why do atoms get bigger as you move down a group or family? So as you go down a group or family, there are more energy levels increasing the size of the atom. And you can see this in all of these different atoms. As you go down a column, they're going to get bigger. And you can see each ring is a new additional energy level. They're getting more and more energy levels as you go down. So atoms getting smaller as you move left to right. So the atoms are getting smaller as you go left to right on the periodic table because there are more protons pulling on the same energy level. So you can see here lithium has 3 protons pulling on this energy level, which is energy level 2, whereas neon, which you can't see the number in here, there's 10 protons pulling on that same second energy level. So it pulls them in really, really tight. All right, what happens to reactivity of metals as you go on the periodic table? So first we're going to talk about going down. And we saw this when we looked at the reactions of sodium, potassium, and lithium. These guys, actually it's lithium, sodium, potassium, if we're going down. And the reactivity increased a lot. And then we also looked at going across the periodic table. We looked at this row here, I can't really read the letters, but we went over this way and the reactivity decreased because they're getting smaller. So down a group or family for metals, the reactivity increases, and going across left to right, the reactivity decreases because the atoms are getting smaller, the electrons are more tightly held, therefore our reaction slows down a little bit. All right, let's talk about reactivity of nonmetals on the periodic table. So nonmetals, of course, are going to be gaining electrons, and basically to pull in electrons, smaller is better because the pull is better. So for us, we can see it gets smaller this way and this way. So what this means for reactivity is down a group or family, the reactivity decreases, and across a row or family, it increases. All right, so size for atoms, which is better? So for metals, we know they're losing electrons, so the more loosely held, the better for them. So bigger atoms are going to lose their electrons more quickly. And for nonmetals, it's the opposite. Nonmetals want to pull in an electron. You can see it grabbed one of sodium's electrons right there. And so to pull in those electrons, it needs to be closer to the nucleus to pull them in more effectively. So smaller is more reactive for nonmetals. All right, so why are bigger metals more reactive? This is just kind of summing up everything that we've talked about. So we know metals lose electrons in a reaction. The bigger the metal, the more loosely the valence electrons are held. The more loosely the electrons are held, the more easily the electrons are lost, making them more reactive. So if we look at the picture to the left here, this element, cesium, is the biggest metal in this picture, so it would be the most reactive. All right, so for nonmetals, why are smaller nonmetals are more reactive? Make sure to include why they are reactive, how smaller atoms hold their electrons, and why this makes nonmetals more reactive. This makes smaller nonmetals more reactive. So we know nonmetals gain electrons in a reaction. The smaller the nonmetal, the more tightly the valence electrons are held. The more tightly they're held, the more easily electrons can be pulled in, making it more reactive. And of course, nonmetals are a little more complicated than metals because we have our group 8 here as part of the nonmetals. These guys do not react, hence noble gases. They are not going to mix with the common elements. So what we have here is fluorine is actually the smallest nonmetal that reacts. And again, smaller is better because we're pulling in electrons, so the valence level is closer to the nucleus, and fluorine can really easily pick up that last electron. And that's it for the review. I hope this helped.